Hello everyone, this is the lesson y'all have been waiting for because you're going to get to start using your derivative shortcut rules. But before we do that, I'd like to look at something with your calculator, something we call the numerical derivative. Okay, so if they ever ask you for a numerical derivative, that's when they want you to use the calculator. So if you remember in guided practice the other day in class, we found that f of x equals the square root of x plus 1. We found that f prime of 3 was 1/4. We're now going to do that on the TI Inspire, and we're going to show how that works. Okay, and then we will also use f of x as the absolute value of x, and we're going to use the numerical derivative to find several values, and then we're also going to graph. Okay, go grab your calculators. Okay, so we're going to choose a calculator page. I've shown you how to find the derivative when you've already have the graph present, but we don't have the graph now. We're going to use the template key, and notice here's the D box of box, and we choose that. That's our derivative template. We want to find the derivative with respect to x of, so I'm going to tab, and then my function was the square root of x plus 1, and I'm going to tab out. Now, if you press enter on this, you're not going to get an answer. We want the derivative at a specific x value when x was 3. So we're going to control equal so that we can get to this such that symbol. This up and down straight line is such that. So the derivative with respect to x of the square root of x plus 1 such that x equals 3. And press enter. And there's that 1/4, same that we had. Okay, now we're going to look at f of x equals the absolute value of x, and we're going to find the numerical derivative. So we're going to do the same thing. We're going to use our D box of box, and we have the derivative with respect to x of, and I need to tab in here, and I need my template key again to get my absolute value of x. Tab outside your function, control equals for such that, first we want the derivative at 2, so x equals 2, and we press enter. The derivative is 1. No problem. Okay, we can do this again. Menu, D box of box, and then we have the derivative with respect to x, tab, template key, absolute value symbol, put the x in, tab outside. Now we control equals such that x equals, and we want the derivative at 3, so we hit enter. There we go, and our derivative is also 1. Now we can also, the next one I want is the derivative at -2. I can save myself a little work just by arrowing up and hitting enter, and then just back over in between here, stick in that negative and hit enter. Now my derivative at -2 is -1. When I want the derivative at -3, I'm going to arrow up, hit enter to copy it, get in there between the equals and the 3, sneak in a negative, and press enter. There we go. Now let's say I want the derivative at 0. There it is. See this little symbol here? That's telling you something's wonky. It's undefined. The calculator's going to tell you undefined because the derivative does not exist there. That derivative does not exist. Now, I'd like to go to a calculator page. So I'm going to add a calculator page, a graph page, sorry. I'm going to add a graph page. And if I had the absolute value function of x graphed, I do want to show you this also. If I had this graphed, I could go back here and do this derivative with respect to x of x, tab, and I could say f1 of x. So if you already have it in the function, there's no need to recopy. Let's do x equals -3 because I can still see that on my screen. There it goes. It gives us the same -1. Okay, so that's another way you can. So there we have our absolute value, but I really, you know what, I want a clean screen. So I'm going to put in a new graph page. What I'd like to do is graph the absolute value of x. So we can do this in 2 different ways. If I haven't already graphed the function, It's just the box, and we make it x of, and we put in our absolute value of x, absolute value, x, hit enter, and there is the graph. Now what you need to realize, it's not going to show you the open circles here, but we know that the derivative doesn't exist at 0, so it's going to have an open circle here with an arrow, an open circle here with an arrow, okay? Also, since we already on this page had the derivative graphed, we could have, instead of typing the absolute value, we could have, and sometimes it depends on how complicated the function is, the derivative with respect to x, tab f1 of x, and hit enter. With this particular function, it was really easy just to use the absolute value of x. It was more work to type f1 of x, but if you have a complicated function, sometimes it's easier to use that method. Okay. Okay, so now let's go get our derivative rules. So the first one is the derivative of constant function. If f is the function with the constant value c, that means here's our x and y axis. We have a horizontal line that has a height of c. What is the slope of that horizontal line? The slope of any horizontal line is 0, which means that the slope of the line is the slope of the curve, is the derivative, so that the derivative of any constant is 0. That means if I ask you for the derivative with respect to x of 7, your answer is 0. Done. Next up is the power rule for positive integer powers of x. So if n is a positive integer, then the derivative with respect to x of x to the n is bring down the exponent, multiply it by the front, keep the base x, and subtract 1 from the exponent. So the power rule says to differentiate x to the n, multiply by n, and subtract 1 from the exponent. So if I want the derivative with respect to x of x to the 5th, I bring down the 5, keep my base x, and 5 minus 1 is 4. So the derivative is 5x to the 4th. Next comes the constant multiple rule. So if you have a constant times another function of f, so if u is a differentiable function of x and c is a constant, then the derivative with respect to x is the constant times the derivative of u with respect to x. So you keep the constant and multiply by the derivative of the rest of it. Okay, so this says that if a differentiable function is multiplied by a constant, then its derivative is c multiplied by the derivative. So in other words, the derivative with respect to x of 2x to the 3rd is keep the 2 times, now what's the derivative of x to the 3rd? We bring down that exponent 3, keep the x, the new exponent 3 minus 1 is 2. Now we multiply monomials. 2 times 3 is 6x squared. There is our final derivative. Next rule is the sum and difference rule. So if we have two parts, we're adding things together. The derivative with respect to x of f of x plus g of x is the derivative of f of x plus the derivative of g of x. If we're subtracting, taking the derivative of a difference, we take the derivative of the first part minus the derivative of the second. So if I want to take the derivative with respect to x of 4x cubed, I'm going to do 4 times, bring down that exponent, 4 times 3 is 12, keep the x, 3 minus 1 is 2, plus, now I have a constant, the derivative of that constant is 0, so my final answer is 12x squared. All done. Now we have second and higher order derivatives. So the first derivative is y prime or f prime of x or dy dx. A second derivative is written as y double prime, or the derivative twice of y with respect to x twice, or f double prime of x. The third derivative is y triple prime, or the derivative 3 times of y with respect to x cubed, or f triple prime of x. And then anything more than that, it's y super n. okay? Or we'd have f super n of x. That's the nth derivative of y with respect to x, or the nth derivative of f with respect to x. So we're now going to find first and second derivatives. So our first example, we have f of x is x to the fifth divided by 5 plus 2x to the negative 3 minus x. So our first derivative, we're going to do, we bring down the 5. Now remember, we have a constant 1/5, so we keep that. We bring down the 5, keep the x, our new exponent is 4. But some of you are going to say, wait a minute, that's just x to the 4th. And yes, it's perfectly fine if you go right from the function to here. That's absolutely fine. Now we're going to have the 2 times, we bring down that negative 3. 2 times negative 3, right, because it's negative 3, times keep the x, subtract 1, that's to the negative 4. So 2 times negative 3 is negative 6, x to the negative 4. Minus the derivative of x, that exponent is 1. The new exponent is 0, and x to the 0 is 1. So here is our first derivative. Our second derivative, we bring down the 4, keep the x, 4 minus 1 is 3. We're going to multiply. Negative 4 times negative 6 is a positive 24. X to the negative 4 minus 1 is negative 5. And the derivative of negative 1 is just 0. So here is our second derivative. Awesome. Now notice I did leave negative exponents, but I gave you negative exponents in the problem, which is why I let you leave them. Now here's another example. This time we have f of x is the square root of x plus the cubed root of x. Before you take the derivative, you need to rewrite this. The square root of x is x to the 1/2. And the cubed root of x is x to the 1/3. There's that basic algebra that's going to trip you up. We have done no calculus yet. That is not f prime of x, that is still f of x. All we did is rewrite the function. Now, I'm going to take the derivative. I'm going to bring down the 1/2. I'm going to keep the x. 1/2 minus 1 is negative 1/2. Plus, I'm going to bring down the 1/3. I'm going to keep the x. 1/3 minus 1 is negative 2/3. Now, I did not give you any negatives or fractions in the exponents, so you're not going to give me any back in your answer. So we're going to rewrite this derivative. We have 1/2. This negative in the exponent tells me to put the x in the denominator. A 1/2 tells me to take the square root. Plus, I have 1/3. The negative in the exponent tells me to put the x in the bottom. The 2, the top, tells me to square it, and the bottom, the 3, tells me to cube root it. This is my f prime of x. Now I still have to take my second derivative, but we're going to go back to this form to do our second derivative. And we're going to do 1/2 times, bring down that exponent, negative 1/2, x minus, to raise to the, now negative 1/2 minus 1 is negative 3/2. Plus, I have 1/3 times, I'm going to bring down the negative 2/3, keep the x. Negative 2/3 minus 1 is negative 5/3. So this is negative 1/4 x to the negative 3/2 minus 2/9 x to the negative 5/3. But again, you have negatives and fractions in the exponents, so we need to rewrite this. F double prime of x equals, I have negative 1/4. The negative tells me to put the x in the bottom. The 3 is the exponent, and the 2 tells me to take the square root. Minus 2/9. The negative tells me to put the x in the bottom. The 5 is the power, and the 3 is the root. And here is my second derivative. Next up, let's look at these. These are some of the new ones that the AP likes. F and G are differentiable functions such that f prime of 1 is 2, g prime of 1 is 6, and then they give us h of x is 5 times f of x minus 4 times g of x plus 3x squared minus 2. What's the value of h prime of 1? Now before I can find h prime of 1, I need to find h prime of x. So h prime of x is going to be keep the constant times the derivative of f of x is f prime of x, minus keep the constant 4, the derivative of g of x is g prime of x, plus we're going to take this exponent 2 times 3 is 6, keep the x, the new exponent is 1, so I don't have to write it. And remember, the derivative of negative 2 is 0, so I don't have to subtract 2 from the end. So now I have the derivative of h of x. So now I can find the derivative of h at 1. That's 5 times f prime of 1 minus 4 times g prime of 1 plus 6 times 1. So that's 5 times. Now f of 1 is 2 minus 4 times g prime of 1 is 6 plus 6 times 1 is 6. So 5 times 2 is 10 minus 4 times 6 is 24 plus 6. So that's 16 minus 24. H prime of 1 then is negative 8. Nice. Okay, so you like those symbolic ones, right? If you like that, you're going to like the next one. Now the graphs of the linear functions f and g are shown. They're linear functions, which means they have the same slope everywhere. So if h of x is f of x plus g of x, when we want to find h prime of x, we take the derivative, that's f prime of x plus g prime of x. But wait a minute. F prime of x is just going to be the derivative of this line, which is the slope. Well, what's the slope of this line? This line, let's see, from here to here, we go up 1 over 2, up 1 over 2, up 1 over 2. This has a slope of 1/2. So f prime of x is 1/2. Plus, now we need to find g prime of x. So g prime of x, we're going to find the slope of this is going to be g prime of x. And let's look at this slope. This is going down 1 over 1, down 1 over 1, down 1 over 1. This one just has a slope of negative 1. So that means that h prime of x is just 1/2 minus 1, or negative 1/2. It is always a numerical value for this problem. All right, next up is the product rule. So if we have the product of two differentiable functions, u and v, then the derivative with respect to x of u times v is u times the derivative of dv dx plus v times du dx, which is very confusing. They're just different letters. Do not let it confuse you. It's keep the first derivative of the second plus keep the second derivative of the first, which is very much like this, only I switch the order so that it makes the next rule easier. But the derivative with respect to x of f of x times g of x is f prime of x g of x plus f of x g prime of x. Derivative of the first, keep the second, plus keep the first derivative of the second. So here's an example. Y equals the quantity x plus 2 times x minus 5. We're going to find dy dx without using the product rule. So without using the product rule, we would have to multiply x plus 2 times x minus 5. So that's going to give us x squared minus 5x plus 2x minus 10. So y is x squared minus 3x minus 10. Now we could do the derivative. The derivative of x squared is 2x, minus the derivative of 3x is 3, and the minus 10 has a derivative of 0, so we would be done. Now, we're going to take this same function, and we're going to use the product rule. So the product rule says the derivative of y is dy dx, and we do the derivative of the first. The derivative of x is 1, and we keep the second part, x minus 5. Then we add, and this time we're going to keep the first part, x plus 2, but the derivative of x minus 5 is 1. Now, since both of those were 1, it's not that difficult to multiply. It's just x minus 5 plus x plus 2, and a lot of you will even skip that step. I would. Combining like terms, I have 2 x's minus 3, and we do get the same answer. Isn't that awesome? Okay, one more rule would be the quotient rule. At a point where the denominator is not 0 and the quotient is y equals u over v of two differentiable functions is differentiable, then the derivative with respect to x of u over v is v times take the derivative of the top with respect to x minus keep the top, the derivative of the bottom with respect to x over the bottom squared. And if you're using f and g's, it's f prime of x times g of x minus f of x, g prime of x over g of x all squared. Or if you're taking the derivative with respect to x of high over low, it's low d high minus high d low over low low, or low squared. Okay, so let's try an example. So if we have y equals 5x plus 3 all over 2x plus 1, we want to find the derivative. Now the derivative of y is called dy dx equals, we take the derivative of the top. The derivative of 5x plus 3 is 5, and we're going to keep bottom, which is 2x plus 1, minus, now this time we're going to keep the 5x plus 3, and the derivative of the bottom, derivative of 2x plus 1, is 2, and we put all of that over the bottom, 2x plus 1 squared. Now we have a little bit of algebra to do. First thing is we distribute the 5. So 5 times 2x is 10x, plus 5 times 1 is 5. Then we're going to distribute this whole negative 2. So negative 2 times 5x is negative 10x, and negative 2 times 3 is negative 6. Do not multiply out the bottom. Leave that as the quantity 2x plus 1 squared. Combining like terms, our x's are going to add to 0, and 5 minus 6 is a negative 1 over that quantity 2x plus 1 squared, and that is our dy dx. Okay guys, we did a lot of rules today, all of our basic differentiation rules. We also learned how to do the derivatives on the calculator, both numerically as well as looking at the graphs of the derivatives. That's a lot of stuff we learned. You do need to know these rules, and we are going to practice them in class over the course of the next few days. All right, guys, have a wonderful day.